Good afternoon, everybody. This is the Utah Scientific IT Essentials webcast. We're going to get started in just a minute. We just want to make sure we give everybody maybe a couple of minutes to join. Looks like our numbers are going up quickly here. We're at about almost 30 participants right now. So I won't wait long. We'll get started pretty quickly here, but just to give people a chance to kind of log on here, I might wait another 20 seconds or so. Actually, I'll just go ahead and start doing the intro, and because you're not here to see me anyway. So let's talk about what we're going to be talking about. Again, this is Utah Scientific IT Essentials webcast that we're doing. My name is Brett Benson. I am the Director of Strategic Accounts at Utah Scientific. I'm actually coming to you from Florida right now. So if people walk behind me and everything, we're down here on some sales meetings. So that's what's going on. Nothing too crazy going on behind me. We're going to talk today about, again, IT essentials. And Scott Barella, our CTO at Utah Scientific, is going to do the presentation. If you know Scott, you know he knows a lot about IP video. He knows a lot about IT. He's currently our CTO and VP of Product Development. He's also Deputy Chairman of AIMS, and he's on the SMPTE group dealing with getting all this stuff to work, 2110. So he's going to talk a lot about some of the IT considerations you have in moving to video over IP. This is the first of a series of IP conferences, web conferences we're planning on doing. This is going to be pretty elementary, and then everyone will get a little more detailed from that point on. Couple housekeeping notes real quickly. If you have a question, you'll notice down at the bottom, there's a button that says Q&A. Go ahead and type in your question, and I will read those questions at the end to Scott, and he'll answer those questions personally. Don't worry, we won't say names unless you want us to say your name, but we won't say names, and you know how it is, there are no bad questions. So go ahead and just type those questions in. We'll cover those at the end. And at that point, I think we'll just go ahead and move on. So go ahead and introduce again Scott Barella, our CTO at Utah Scientific, and take it away, Scott.
Okay. Hey, thanks, Brett. Appreciate you all showing up to our first of a series of our IT webinars. I wanted to preface this thing. If you see my screen, it's a rudimentary level. So if you're already familiar with IT, this is not the webcast for you. But if you're a little confused and you really don't understand and you wanted a little more background to it, that's what this whole thing was created for. So at least it's a start to get going, and we'll follow that up with an idea we have at the very end here. So without further delay, we'll carry this on here. We're going to cover IT essentials, and it's essentially unbundling Ethernet for studio video over IP. So this is uncompressed video, which is the first time we've done this on IP. Actually, not the first time, but this is mostly about uncompressed video, where IP has been traditionally used in compressed environments. This is uncompressed, so the payloads are a little different. But we'll get in that just a little bit. So why IP? A lot of people want to ask about, geez, why do we need to do this? Well, it's an evolution, basically, and we continue to keep moving this thing forward. In my days as a kid, we sat around the television and watched black and white. I certainly still remember those days. Analog to digital was a big one in my early career. SMPTE 259 was the base level for that one. And we also transitioned from standard definition to high definition, and we had a standard based around that one as well. And we continue to have those standards as we move into higher definition formats. So the next chapter is obviously the move from SDI to IP. So SMPTE 2110 is basically a standard that's based entirely on Ethernet packets. There were some previous attempts, and you may have read about them or seen about them or heard about them. SMPTE 2022-6 is certainly one of the first attempts, and a thing called audio-video bridging that came out of Europe, out of the IEEE 1744A initiatives. Those were all based on sync pulses that were inherent to SDI, and so SMPTE 2110 essentially bases this on Ethernet packets rather than sync pulses. And this is really the difference between this standard and other ones attempted prior. So Ethernet is the very, very key of the foundation for SMPTE 2110. So I thought we'd take some time. Again, this is elementary. So the thing that happens in Ethernet is we have to talk and carry on in subnets. I like to think of subnets as streets, and you see this sign here at 3rd and Main. This is where all the addresses live. So if you can imagine having houses along the 300 block of Main Street, that's kind of how we're going to group those first initial addresses. And to get into that, we use actual private addresses. Now, these are addresses you might be used to if you have a PC at work, or if you're on an internet at a hotel or whatever, and you may look down to see what your IP address is. These are private addresses, and addresses that are used so that you're not a public IP address, but rather hidden behind a firewall or a router. And we can use other numbers that we don't have to tie up public numbers with. So these things come in various sizes, as you might imagine. A Class C is relatively small and the most commonly used in the 192.168 subnet. Class B, slightly larger. We use 172 numbers for those. And Class A in large corporate environments where you have a campus set up. This is used in universities and corporations, and they are referred to as Class A private subnet range. So these are kind of the backdrop of how these addresses get used and how they're actually put into play. So we'll just take the first one, the Class C address example. And here I use a common address of 192.168.1.10 as our first address. And you might think of that as the house that you're in. Maybe the second address would be the next one up, which would be 11. Think of that maybe as the house across the street. Evens on one side, odds on the other. And the one, the side street down the road there, or the alleyway, might be the gateway address. It's like another street, and we're on 3rd Street, then maybe it's like Main, the intersection of it. But the 192.168.1.10 and the 11 would be house 1 and house 2. So in this example used as a house across the street, these are how you kind of think about these two. Now notice that the first 3 numbers are the same, and that's really kind of the key to the subnet. So the way to remember it is that you have to kind of be in that same subnet. Now obviously if you have it larger, we can increase that and we get into what they call a mask. But for today's discussion, we'll make it really easy to understand. So we use a command line interface, which is typically used, if you remember the days of DOS, we used it all the time. And then when Windows and graphics formats came out for computers, these command lines started to disappear. But lo and behold, they're still there. And we use one to confirm the one address to another. So we use a command line command called ping. And I like to think of it as 2 tin cans. When you try and make sure that you got somebody at the other end and you want to see if they're there, you can raise your tin can up, the other guy listens, and you can say, hello, do you hear me? And the other guy turns around and he says, yes, I can. So in that sense, you know that you have a communication or a means to at least start communicating once you have a basic response and transmit established. So the way we get around making sure that we can go out into the internet, we use a gateway. So the way to think about it is that the little picture there in the corner there, where you've got a gateway out to the backyard there. You open the door and you're there into the internet or wherever you're kind of aimed to. But that address is how you know you can go to another place, another street, and that is a gateway address. And usually it's assigned as the last first number in the last octet, which is 192.168.1.1. That last one there is typically the gateway. I've seen them as other numbers, but they're traditionally used that way. So a local area network is how we would communicate with other houses along the streets. The way to think about that is you've got Main Street, for example, that we started with, and you've got 10 and 11 used. Well, maybe the neighbor is 13, and then 15, then 17, or all the numbers that are in that subnet are all along Main Street, so that you have communication now to all those people on that same block. And that's the way to think about a local area network. A lot of companies actually use the same methodology for creating a local office internet, where you have several PCs. In the example here, we have a server and we have 3 little workstations and a printer and a router out to the internet. it's really simple that those three machines and the printer are all on the same subnet. So that's how they actually communicate with one another. Usually they're confined physically. That's how we kind of keep it organized in our own mind, in that everything in the office building would be considered a part of the LAN, and anything in it could be used, right? Well, where it gets a little complicated is where you start to have more than one room or more than one building, or another floor, for example, within that building. And there we use a wide area network, a WAN. Typically, that's where we combine either a larger subnet or we can actually divide them up if we want to. We have some choices there, but in most WANs, they typically create like little LANs to connect together, and that's how that's used. So in the broadcast environment, this would be something where you'd have maybe a studio at one location and another studio maybe downtown, and that would be connected together using a WAN, or a wide area network infrastructure. It's also true that they use the same sort of methodology when they're trying to do campus buildings, where you've got the health and science building in one, maybe the student arena in another, and then you have the mathematics building in another campus building. And all those buildings are combined together, and they're used a wide area network so that you can kind of still keep them separate, but you can still keep them connected together. Now, for broadcast, when we use this for video and we use it for audio, we're real familiar with the idea of a unicast. And in IP, this is really simple to understand. You've got one transmitter and you've got one receiver. So if the red dot is trying to talk to the green dot, you simply connect them together. And in our example early on, we would have the 10 address being the transmitter and the 11 address being the receiver. So one speaks and the other one listens. And that's basically the confines of what a unicast is. Well, that works fine for some applications, and actually a very few limited, but we're more used to speaking to many things, especially when we're in a broadcast center, right? So that's where multicast comes into play, where you have one transmitter, but you have several receivers or many receivers, right? So you can talk to several addresses. So if you're the transmitter at 10, you could speak to 11, 12, 13, 14, 15, whatever. As long as you're the speaker and they're the listeners, those two can be joined, and that's the concept essentially for multicast. And this is how we would move video, for example, from a point A to point B, C, D, and E, where one's maybe a monitor, maybe one's a production switcher, maybe one's another landed spot on a multi-viewer or what have you. There would be several places where that single set of video might be used multiple times, and that's the concept that we use for IP. But we're still confined within the subnet. So the way that it listens to the same transmission is we use a thing called multicast address. And that's this number here that you might see from time to time that I have in the slide here is 239.1.1 at port 10,000. So even though we're speaking from that one IP address, we're actually sending it over the multicast address of 239.1.1.10,000, so that each of these receivers, 11, 12, and 13, as long as they're tuned in to 239.1.1.10,000, they'll hear what we're sending them. The method that they actually get joined together is called IGMP, or the Internet Group Message Protocol. This is something inside the switch or the router. This is actually joining the receiver and the transmitter. So really the receiver says, hey, I'm looking for a certain chunk of traffic. Do you have this on the switch? And the switch says, sir, we have that. Do you want to listen to it? And you say, yeah, I do. And so that communication back and forth is how the IGMP protocol works. But it's as simple as that. There are really two versions of it. The version 2 is more commonly used. It's very basic. And version 3 is where you have a lot more sophistication to it. You want to keep track of that. So in that sense, it's fairly simple in terms of joining the receiver to the transmitter. So the next up is what they call virtual LANs. And the way to think about this guy here is that it's still the LAN concept, where you have a couple of devices or groups that you've logically done. But instead of using a separate switch for each LAN, we actually do it in one switch, and we divide those ports separately. And the way we do that is we actually kind of create mini switches or many switches within one single switch. And that allows us to do even more groupings on a virtual setting, so that virtual VLAN 1, for example, might have a couple of PCs, and VLAN 2 might have another couple of PCs. In our case in video, we might have cameras and so forth that are associated with Production Studio 1 in VLAN Group 1. But in Master Control, we might have different objects, and we might group those into VLAN 2. And the way that we would actually segregate and move that traffic around is within the switch, by actually making gateways and clever little ways to connect those VLANs together. But that's the idea, and that's how we're going to do it in SMPTE 2110. Now, it's important to go over the idea of a pipe size, right? So that all Ethernet, just because it's Ethernet, doesn't make it the same. So if you know your HDSDI and your SDSDI and the payloads thereof, that'll give you a good, healthy idea of what size of pipes you're going to need, right? So in the beginning of Ethernet, you had what was confined to be a 10 megabit pipe. So think of a small pipe, right? That's how we started. As time went its merry way, the pipes got bigger, and we had 100 megabits, and it was called fast Ethernet. And then here lately, in most offices, we connect things together with 1 gigabit Ethernet. But the pipe size has to be able to accommodate the payload. In our case, we know that video is going to be fitting into there, and they're a lot larger than we're used to, especially uncompressed. And so 10 gigabits per second and 25 gigabits per second pipes will be needed for those payloads. So here's an idea. So at least here gives you some notion of what we're dealing with here. SD, which is how we started, is 270 megabits. And so that would easily use the video switch of a 1 gigabit switch. And that works fine because we have plenty of room. But when we jump up to HDSDI, we go above that 1 gigabit port. So we're going to next go up to the next size of pipe, which is 10 gigabits. Now that does mean that we can fit more than one HDSDI into one pipe. It means we can actually fit 6. And as 3G starts to take off in terms of 1080p with HDR or whatever, that's going to be 3 gig per second and still fits within the 10 gig Ethernet port. However, UHD and 4K and 8K, those are going to be much larger than 10. We'll use the next size pipe up, which will be 25 gigabits per second. They're even talking about 50 gigabit pipes and much larger. As time goes its merry way, we'll start to size up these uncompressed payloads into these sizes of pipes. So Ethernet packets are based, or Ethernet in general is based on packets. And by that, we have to obey very, very strict rules. It's how the internet works. It's how we actually get an office connected together, because those packets that are emitted onto the network have to obey certain ways of traffic. So in my little slide here, you can see that you know, if you take an off-ramp, there's a certain method of how you get onto the on-ramp and how you yield the traffic and so forth. And those are similar rules that we have when we're using Ethernet. So in the 2110 architecture, we still have to pay attention to all of those Ethernet rules because they were there first and we're now second. We have to make our video fit those traffic rules. It's based on the open systems interconnection model. And without getting too elaborate here, this is how everything is done in terms of Ethernet. And we choose certain transports and certain networks and certain presentations. The ones to the far right, where I listed it down at the physical level, called the phi level, that's where we actually start. That's where you have ones and zeros, and you start to aggregate signals on the Ethernet. And then the Ethernet is going to be the methodology. Even though there's other methodologies available, we're going to use Ethernet. Why? Because it's common. Internet protocol, the IP part, if you remember the TCP IP, well, we're going to use the IP. That's how video has been used traditionally. And we use the Universal Datagram Protocol, the UDP packet. And this is how we're going to actually transport the actual video. But video has to happen line by line, frame by frame, in a very dictated sequence of events. And that's how we've done a video from the very beginning, and that's the way we continue to do it. But in the Ethernet environment, we didn't have really anything was common, so we use what they call the RTP protocol, the real-time protocol. And with it, we're able to actually sequence the packets in the proper order so that we have the line 1 heading first, line 2 heading second, so forth. And we actually bury that within the UDP packet. So I'll go back one slide. If you look at the structure from the PHY level all the way to the top, from PHY to Ethernet to IP, UDP, and then finally RTP, this will happen for both audio, for video, and for data. So this same thinking is how we're going to actually move the essence data around the fabric with respect to what we're going to do with it in the video and audio environment. But we still have to pay attention to that. So we use the RTP method. In here, we can fit 7 RTP packets within a UDP. So if you're looking at it with an analyzer, you'll actually see UDP packets first. And if you bury down underneath the UDP packet, you'll find these RTP packets. And in there, we see the first 1, 2, 3, 4, 5, 6, 7, and that's a sequence number, so that each number would follow the second. So if you're missing one, it knows to wait and gather up the other one before it goes forward. The last number, the really long number, is the actual timestamp, and we get that from a thing called Precision Time Protocol. That PTP timestamp is actually the magic of what we've done within SMPTE 2110. It's able to align the video and the audio, and we can also use it for timing, but it's a way of actually timestamping each packet. This was never been possible in SDI, so we have some advantages in this new topology where we didn't have that before. It's quite interesting if you start to think about it. In the 2110 format, we actually have a separate essence stream for each of the data types. So we have a separate essence stream for video, a separate essence stream for audio, and there could be more than one, could be 2, could be 3, could be up to 20, doesn't matter. But they're a separate stream. And then there's a separate stream for ancillary data, where you'd find closed captioning, where you'd find time code, or automatic field or frame or field detection, AFDs. All the things that we used to bury in the VANC area in VBI, we actually have as a separate stream. So you ask, well, why do we have to have separate streams? Well, in the old days, we used to have a separate audio and we had a separate video. This goes back to the days of analog. When we got into SDI, we found a clever way of embedding it. Well, we wanted to actually be able to have a little bit more flexibility. So we created a system here so that the video is separate. So if, for example, a DVE device that you're wanting to squeeze the video down and you only need to grab the video, you can grab just the video stream. You don't need to grab the audio and the data stream. If, for example, you're doing a mix for the show and you need to adjust volume level, then you only need to grab the audio. And that's the beauty behind the system. It doesn't require you to de-embed and embed each of the elements. You have them all separate so you can do with whatever you want with them, and you can actually move that traffic around. Now with it is you have a separate address. As we started to our simple examples early on, we would have a separate multicast address for audio, a separate multicast address for video, and a separate multicast address for data. So you're wondering, how does that all connect together? Well, there's actually 2 IP ways to do this, right? So you'll have a management layer, which will be a subnet of, I picked out the example of 192.168.100, and that's how we actually control the device or the transmitter. And on the far right, I have a whole bunch of receivers. So I have 4 transmitters on the left, and I have 4 receivers on the right. And I've identified them by number, so if you kind of want to look at the details of that, you can. But the idea is that the top management switch would control the device, and the center switch is actually the audio and the video and the data that's being traversed from one object to the other. I put the grandmaster at the bottom because remember about that timestamp. It actually has to be available to the transmitter so they can actually properly timestamp those packets. So that's how that all works together. This is a very simple diagram to give you an idea of how this is actually being pulled off, so that you can understand from a very elementary level how the basic system actually connects to one another. So how do you actually use all this IP? A lot of good questions, and we've been traditionally using them in an SDI environment. We have some conversion products that we've been busy working on over the past year or so here at Utah Scientific. And if we take those SDI signals and we convert them to IP, we actually create somewhat of a hybrid environment. So one of the first applications that's starting to come up is multi-viewing. Multi-viewing is a very simple use case. And for some more examples of that, I'm going to hand this back over to Brett, where he's had a very interesting way of getting you guys started so that you can start to understand this technology and be able to manipulate it as well.
All right, thanks a lot there, Scott. And really quick, I did get one question that came up. Actually, I was texted directly with this. Somebody wanted to know if they got pulled off and on this presentation, if they would be able to watch this later. And the answer is yes, it is being recorded. So if you've had to jump in and out and answer calls or do whatever you had to do for work, there will be a recording of this that will be available, that will be made available after. And also, if anybody has questions, go ahead and enter some of those in on that Q&A button. And I'll just talk a little bit about what we're doing at Utah Scientific to help make this easier to try and learn how to work with IP, because that's one thing that you know, doing all these interops that we do as a company and installing some video over our IP technology with some stations, we've learned a lot. And there's some important things to know as you start implementing these devices out there. And so Scott, of course, has covered the base level of that, but the best way to learn with this, of course, is to use it. We have what's called Utah Scientific, an IP starter pack. There's 3 parts to this. There is something to give you IP video, 2022 IP video. There's a 10 gig switch, and there's a multi-viewer. Now, as far as what gives you the 2022 video, that can be, if you're a current Series 2 customer, that can be a card that you just slide right in your Series 2 router. If you're not a Series 2 customer, then we have a chassis that will convert SDI to IP 2022. You take those videos, you feed the 10 gigabit switch. And from that switch, then you feed a multi-viewer, and it's all done in IP video. Now, the beautiful thing about this, and where this really, I think, light starts to turn on how this can be used, once that video is in the IP switch, it's there. And so you can take video and feed a multi-viewer, but then you can take that same video right out of the switch and feed something else and redistribute it, basically turning that switch, that 10 gig switch, into another router or into another crosspoint or DA or however you want to describe it. But it allows you to reuse those video signals as well as, of course, feed a really nice multi-viewer. This product, the IP starter kit, is less than $25,000 for all the equipment that you're going to need. And of course, we can give you more information on that if anybody is interested in that. I know you're not on here for a sales call. So if there was more information that anybody needed, if you had any questions, go ahead and type in those questions. Other than that, I'll go ahead and throw it back to Scott.
Thanks, Brett. This series also is highlighted with a white paper, and we make that available to all of our customers or anybody who's interested to review what we went over today. And it has a little bit more detail, but it's a very rudimentary base starter, so that you understand sort of the base concepts. So as larger concepts move forward and you have a little more complexity to it, you at least have this as kind of the foundation for it. So that's my white paper there. It's all IT Essentials, Unbundling Ethernet for Studio Video over IP, and it's available on our website. If you have specific questions that you might be afraid to ask or whatever, just shoot me an email, and I'd be happy to answer the best I can for you, or at least give you a little bit more insight. I want to thank you all for taking your valuable time and sharing it with us. And we wish you a good day, and hope everything goes well. Thanks.